Hello everyone, welcome back to the matrices 8.7 transition matrices and also the lastly matrices. So today what we're gonna do is we're gonna give you some examples to do. I'm gonna try to split out 8.7 to two videos. So today we're gonna do transition matrices first, and then next session we're doing lastly matrices. Um, So before that, what we're doing is we're gonna show you guys how to calculate the a to the power 3, b to the power square, c to the power 0. So you guys should be able to understand how we're gonna try to solve that. So what we do is you guys can figure this out to define the a and b and c matrices, and you just tap the a to the power 3, b to the power square, and c to the power 0. They give you the answer straight away. Now we're going to talk about the transition diagram and the transition table. So transition matrices are based on the transition table and diagrams. So let's have a look. If you remember, you always remember this one is from, and on the horizontal one is to. Okay, so you can say. Um, So what we do is we start with the from to. Okay, so from warehouse A to warehouse A means this part 0.7. So from warehouse A to warehouse A, from warehouse A to warehouse B, which is you are on the top, which is 0.3. And then from warehouse B to warehouse A, which is opposite way, 0.4. And they're from B to B, which is 0.6. If you're adding 0.7 to 0.3, that always equal to 1. 0.4 plus 0.6 equal to 1. Okay? That's the main part. So let's have a look at what we have here. What we do is I'm going to try to show you how to create a transition matrix from the word equation and the diagram. So always remember, you don't have to write from and to once you're getting it. So what we do is I have the A to B, right? So from A to A, which is 0.32, and from A to B, which is 0.68, from B to A, which is 0.45, and from B to B is 0.55. Yeah, so that's the transition matrix from the diagram. And another number of the train, the carriage is the operation between two dots, not two stops. And the end of the redo is north and south from and to north and south. Okay, so what we do is let's have a look. So 40% that start at north end up at south. Sorry, the end of week 40% of the carriages, which is from starting at north and up south. Start north to south, which is 0.4. And 25% start from north to north. Start from north to north, 0.25, so which is 0.75 and 0.6. That's it. Okay, that's a transition matrix. Now we're going to talk about the vector power of transition matrices. So initial state matrices means S0, that's always, or V0, or N0, or A0. So the initial distribution of the vector, which is we involve the T transition matrix, and then distributions of the vector, the one transition, the matrix product, T times the S1. So after one transition, that means S1 equal to T times S0. After 2, that means S2 times T S1. So clearly we can use the recurrence relation, which we did before. Transition matrix for the transition matrix for the recurrence relation will be Tsn plus 1 equal to T times Sn. Remember, Sn always the column state matrix, which is the column matrix. And let's have a look at the distribution after the large number of the distribution transitions, which is equal to t to the power n multiplied by initial state matrix. So let's have a look at this question. The survey showing 75% of the customer will be purchasing from A and then closer to the A, the previous months. So from A to A. So will be from A to A, can I just say A, B, so T transition equal to A and B. I forgot, but I'm not forgot. I say like I don't have to write down from and to if you're getting used to it. So 75% is from A to A. So this month and next month. So can I just say 0.25 will be equal to from A to B. Another one, which is we have another part of the graph will be 80% of this time the purchasing from B and to B. So 0.8, 0.2. Adding all together have to be 1. That's the transition matrix. Now we're going to talk about S0. Let's have a look. Question A. Matrix recurrence relation determine how many customers will be purchasing their groceries from A to B, from A and B, and after 2 months. And if 300 customers start from A, 300 start from B, can just say this one will be A and B, 300, 300. Yeah. So after first 3 months, 2 months, end up 2 months. So T1 times S0 equal to S1. So first month is that equal to 0.75, 0.2, 0.8, 0.25 multiplied by 300 and 300. And that equal to can't remember, but I can show you in the calculator real quick. Okay. So I can just say 2 by 2 matrices. Yeah, 0.75, 0.25, 0.2, 0.8. Sorry, 0.2, 0.8. And control variable and T in time. Yeah. So, and then what we do is column matrices S. So we do 300, 300. And we say is equal to S. So control variable. Perfect. And T times S equal to 285 and 315. Yeah. That's the first one. And then now what we do is we're using that as equal to control variable as equal to S1. So now what we do is T times S1 will equal to your control variable. That will be equal to 2 months away. So after 2 months, 276 people are going to store A. And 323 people are going to store B. So that's the answer for the first part. Second part, so we're going to calculate 6 months. So now what we do is just use S6 equal to T to the power 6 multiplied by S0. So that will be equal to, after 6 months, what is going on about these two? So So 2 to the power 6 multiplied by s. So control enter. So you will say 268 people are going to the first door, 332 are going to the second. So this is the type of situation, as we say, is your answer. Yep. So we use a CAS calculator. Yeah, and this is a transition matrix. First part. So second part, we're gonna talk about Leslie matrices and also something with the adding on the difference with the curling, restocking stuff, and which is using the other column matrices to talk about. So I'll see you guys in the next session.